If you've been following the Astrum Answer series recently, you'll notice that we've talked a lot about how the universe is structured. Filament structures of galaxies being pulled apart by the universe's expansion, with bubbles or voids forming in the gaps. Because of the universe's expansion, everything is moving away from everything. But of course, this isn't totally true in practice due to a mysterious force called gravity. Gravity is a pulling force, or technically, it is the curvature of space-time caused by uneven distribution of mass. On very small scales, gravity is hardly relevant at all. I don't feel any pull towards objects around me, only towards the Earth because it is so massive. Celestial objects close enough to the Sun are most influenced by its gravity, and all stars in the galaxy orbit around a supermassive black hole at the galaxy's core. But it doesn't stop there. You've probably heard that the Andromeda galaxy is hurtling towards us. How can that be when everything is moving apart? Gravity. Objects that are close enough together with a large enough mass are pulled towards each other by gravity faster than the universe can expand. This is why we have galaxy superclusters, and in fact we are part of one. Gravity is keeping these galaxy clusters bound together, meaning over extremely large timescales, collisions aren't totally unusual. In fact, a new theory has recently been proposed that the Milky Way may have recently experienced a collision with a large Magellanic Cloud-sized diffuse galaxy called Antlia II. Scientists have discovered that the Milky Way has ripples consistent with it having had a collision in the past, but we couldn't pinpoint what it collided with until Gaia discovered the Antlia II galaxy hidden behind our galactic disk. This makes it very hard to spot, as although it is massive, it is very spread out due to the collision, and being behind our galactic disk makes it hard to see due to the stars and dust in the way. But that brings us on to the main topic of this episode, the Great Attractor. In an opposite vein from the supervoids video, where there are regions of space where there is an almost total absence of mass for hundreds of millions of light years in any direction, the Great Attractor is the biggest concentration of mass for hundreds of millions of light years. It is so massive that even though our galaxy is between 150 to 250 million light years away, we and all galaxies around it are currently moving towards it. Estimates put its mass at roughly 1,000 trillion suns, which is enough for many thousands of galaxies. But what could possibly be there that is that massive? Well, for the longest time, it was a total mystery, because, like Antlia II, the region where the Great Attractor is located is hidden behind our galaxy's disk. However, X-ray telescopes can see through the disk, and recent technological improvements and advances in X-ray telescopes have meant that we have been able to detect thousands of galaxies in the region where the Great Attractor is supposed to be. But the mass detected didn't add up. There wasn't enough present to create such a pull. Further analysis has revealed something very interesting, that while we are being pulled towards the Great Attractor, there is something even more massive behind it, located 650 million light years away, called the Shapley Attractor or the Shapley supercluster. Located there are many thousands of galaxies densely packed together with a mass of 10,000 trillion suns, and everything within 1 billion light years is being pulled towards it. On the other hand, looking the opposite direction from the Shapley supercluster, we see an underdense region, where everything seems to be moving away from it, called the Dipole Repeller. It isn't actually repelling mass, but due to all the mass around it being pulled towards more dense regions by gravity, it creates the illusion that it is repelling that mass, although there are some scientists that do claim that an unknown repelling force is at work there. Simply put, we are still in very early days when it comes to understanding the universe. We do observe certain things, like the motion of galaxies, dense galaxy groups, and absences of galaxies in large voids or repelling regions. We observe the expansion of the universe and observe the filamentary structures. But the universe is an impossibly large place, We can only see so far, only live so long. Plus, our technology is limited. We have theories which try and explain what we see, but I really wouldn't be surprised to see these theories change as more data becomes accessible. Some may ask, what's the point then? However, I for one am hugely grateful for the bright minds working on this, as discovering our place in the universe is so fascinating. I'm glad humans have an insatiable need to explore and understand everything around them. This innate sense of wonder and curiosity is what drives the evolution of mankind, and I am excited to witness it.
It takes teams of scientists with the right tools and software to track the stars and superstructures of our universe, but they're not the only things that are tough to manage. Ever feel that way about your business? Then you might need Odoo, today's sponsor. Odoo is an affordable, all-in-one platform with all the apps you need to run your business in one place. It has apps for everything, from accounting to website creation to inventory and much more. For example, its invoicing app is a super easy way to generate invoices by letting you add your customer, add products or services, and set quantities in just a few clicks. You can then send your invoice by email. Your customer can pay the invoice directly via the online portal, and the app allows you to track its payment status, whether it's pending, paid, or declined. Odoo offers a huge constellation of apps, and your first one is free forever with unlimited hosting and support. Looking to simplify the superstructure of your business? Just scan the QR code or click the link below and support the channel while you're at it. Movement through space is inevitable. You might not feel it, but right now you're sitting on a planet that is spinning on its axis, moving you at up to 1,600 kilometers per hour depending on your latitude. The Earth circles the Sun. The Sun moves through the Milky Way. The Milky Way moves through the local group of galaxies. And the local group moves through our local supercluster. And even that supercluster of galaxies is in motion, heading towards the Shapley supercluster, where scientists believe that there is a particularly large concentration of galaxies. I hope all this motion isn't making you too dizzy. But on the grandest scales of our universe, something strange is happening. Scientists have begun to realize that there is not enough mass in the Shapley supercluster to pull us towards it at the rate that we see. About 50% of the cause of that motion is unaccounted for. In 2017, researchers discovered a possible source for the rest of that motion. But it's not something pulling us, it's something pushing. I'm Alex McColgan and you're watching Astrum. Join with me today as we explore the evidence for the region of space known as the Dipole Repeller and try to understand how, in a universe filled with gravity, something can push us instead of pull. Let's start with a little context. It's taken a long time for astronomers to recognize that this motion was taking place. To understand that we were moving, scientists first had to make a map of the regions of space around us. And although we as a species have been mapping the stars since the beginnings of civilization, it was only thanks to Mr. Hubble in 1924 that we proved there are actually stars in other galaxies outside the Milky Way. Before then, although astronomers had seen fuzzy little clusters of light in the night sky that we now know to be galaxies, the common wisdom was that these were gas cloud spiral nebulae within the Milky Way, not something that existed beyond it. Hubble noticed several Cepheid stars, a type of variable star with a cycle of variation closely linked to their luminosity, within one such spiral nebula, and used the fact that this luminosity was very predictable based on distance to calculate very precisely how far away they were. Surprising many, he proved that they do exist beyond the Milky Way. Since then, astronomers have been scrambling to catch up with the new reality of galaxies and superclusters, and set about mapping the locations and distances to every galaxy they could find. Hubble had been studying Andromeda, our closest neighbouring major galaxy, but there were others. By the 1970s, Stephen Gregory, Lard Thompson, and William Tift definitively proved that galaxies didn't just float randomly in space, but converged into superclusters, large filamentary or sheet-like structures that exist between large bubbles of void. They mapped the first supercluster, the Coma supercluster, which covered a region of space 100 million light-years across. A whopping 95% of all galaxies are found in these superstructures. It wasn't until 2014 that our own supercluster, the Laniakea supercluster, was fully mapped. You might be surprised to hear it happened in that order. After all, wouldn't common sense say it's easier to map regions of space closer to us rather than ones further away? Why was it only nearly a century after the discovery of other galaxies existing, and 40 years after mapping the first supercluster, that we finally turned to our own? The answer is that mapping the local regions of space around us is surprisingly challenging, and it's all because of the Milky Way getting in the Milky Way. The Milky Way is full of gas and dust, and these regions are so difficult to penetrate that we can't really see beyond them. Towards the center of the Milky Way, this effect gets so bad that scientists have dubbed the whole area the zone of avoidance. Very little light gets through it. Not being able to see in this area is particularly relevant to our current discussion for reasons we'll get to later. In contrast to our local area, distant galaxies are easier to study, as all you have to do is point your telescope at a single point in the night sky and let it drink in the light. Mapping the area around us requires looking at every point in the night sky. It's proved quite difficult, although astronomers are now getting a better handle on it. Thanks to their efforts in looking at thousands of galaxies in our galactic neighborhood, and by studying galaxies' peculiar motion, or their motion relative to the cosmic background radiation that ignores the expansion of the universe, scientists have been able to group gravitationally bound galaxies into superclusters. At the center of our Laniakea supercluster lies a point known as the Great Attractor, an area 150 to 250 million light-years away from us, that we, in the Milky Way, are slowly drifting towards. Sadly, the Great Attractor lies within the zone of avoidance, so it's tricky to see clearly what lies there. To confound things further, the Laniakea supercluster was also found to be moving. It travels towards another supercluster known as the Shapley supercluster, taking us along with it. At the center of this supercluster lies the Shapley Attractor, which also is believed to be incredibly dense in terms of mass. But frustratingly, this second attractor also lies in the zone of avoidance, making it difficult to see exactly what's going on over there too. Thankfully, as X-ray and infrared telescopes improved, it became possible to take a better look at these two attractors. But this is where the mystery begins. What mass is there is not quite massive enough to account for our apparent motion in that direction, which is why a team of researchers from the University of Hawaii published an article in Nature to attempt to explain this discrepancy. The team was made up of Yehuda Hoffman, Daniel Homerede, R. Brent Tully, and Helene M. Courtois. Together they created a new kind of map of the local universe around us. This time, instead of simply noting galaxies' positions, they highlighted their motions instead. This allowed them to create a map of flow lines, which, after mathematical analysis, allowed them to make assumptions about the locations of masses in our nearby superclusters. Their results were surprising. A lot of our local mass is moving towards the Shapley supercluster, which is what you would expect. But they also found a lot of mass is moving away from another specific region in space. They call this mystery patch of space the Dipole Repeller. Together, the Dipole Repeller and the Shapley Attractor both contribute about 50% to our motion, working together in tandem, hence the name dipole. But how? Gravity is a force that, so far as we have observed, only pulls. What lies in this region of space that allows a push to happen? Could it be a strange collection of white holes? The theoretical opposite of black holes that we've talked about in videos before? Or perhaps some source of anti-gravity? Not quite. The answer is nothing. The dipole repeller is a void, a bubble about 100 million light years across that does not contain many, if any, major galaxies. It's one of the bubbles that exists between the filaments of the universe's structures. But interestingly, our galaxy's current motion lines up much more satisfyingly with the push from this region than it does from the pull of the Shapley attractor, which is a compelling argument in this theory's favor. So how does nothing push? The answer is actually that this could be a pseudo-force more than it is a real one. Imagine a universe where all the galaxies were spaced equally. While the gravity of galaxies above would pull you, the gravity of galaxies below you would do the same. So would the pull of galaxies to your left and to your right. In this way, the varying forces of all these gravities would balance each other, leaving you to not really travel in any direction. You'd be in a perfect equilibrium. But what would happen if we removed the galaxies from one of these directions? What would happen if we added a void? Well, then the scales would tip. There would be one direction that no longer pulled you, leaving the opposite direction's pull to act on you unimpeded. As a result, you would move away from the void as if it were pushing you. Everything near a void will thus move away from it, making it seem to have a repelling gravitational force. It is something of an optical illusion. There is another explanation for why a void space might push you, which might work in tandem with the pseudo-force. The universe is expanding, and that expansion shows no sign of slowing down. In fact, it seems to be speeding up. However, this expansion is counteracted by gravity, and in areas where there is more gravity, less expansion seems to take place. Stars aren't just being pushed away from each other, they're also being pulled together. Conversely, in a void, there is nothing to contain this rampant expansion. As a result, void spaces literally will swell compared to their supercluster counterparts. It might be done by warping the fabric of reality, but this also achieves a sort of push. Since 2017, not much more has come to light about the existence of the dipole repeller. As this is still an expanding field of research, there's some debate about whether it's really there, or how influential it might be on our galaxy's current motion. It is difficult to observe due to the Milky Way's obscuring effect, and there is always a challenge inherent in trying to spot the absence of a thing rather than its presence. However, Tully and his fellow researchers hope that with the aid of future ultra-sensitive surveys in multiple spectrums of light, it will be possible to map out the few galaxies that lie in this void, and generally confirm its existence in the region they hypothesize. We are constantly moving through space, but even the science of space is always in motion. Each new galaxy, along with data regarding its redshift and travel speed, helps us develop a broader understanding of the movement of the galaxy. It's fascinating to think that not all of that motion is caused by the pull of gravity. It might turn out that sometimes the universe just needs a little push to get going.
You may or may not have come across the name Boötes void in the past, described as one of the biggest voids in space that we know of. But what does that really mean? First things first, it is not this image. If you Google Boötes void, this image comes up a lot, but this is actually the molecular cloud Bernard 68, a cloud of dust in space that doesn't allow light from stars behind it to pass through, which I suppose makes it look like a void in space, but it's not in reality. To understand what Boötes void really is, we need to understand some context. We know that space exists outside of Earth. But even outside of Earth's atmosphere, space is quite populated, and astronomically speaking, you are spitting distance from other objects like the moon, asteroids, other planets, and the sun. You can still reasonably use kilometers or miles to measure distances at this point. Outside of the solar system, objects begin to get a bit further away. We start to measure in light years at these distances, a light year being 9.46 trillion kilometers. At this scale, we can see that there are plenty of stars in the near vicinity to us. All the stars in our galaxy make up the Milky Way galaxy, a large structure roughly 150,000 light years across. Beyond the Milky Way are more galaxies, the closest big one being Andromeda at 2 million light years away. Beyond that, we see the local area of galaxies that we are part of. What I want you to pay most attention to at this point is the clustering and banding of these galaxies. You'll see that they aren't evenly distributed. In between all these galaxy groups are voids, where there are only a few galaxies dotted around the place. These are just small voids, being only tens of millions of light years across. Zooming out once more, we start to see this banding happening on a grand scale. At these kind of distances, we begin to see that the universe tends to have a kind of web or filament structure made of galaxies. In between these huge clusters and filaments, stretching for hundreds of millions of light years, are supervoids. One of the biggest that we know of being Boötes void. At 330 million light years across, a typical region of space would find about 2,000 galaxies within that volume on average. But this doesn't mean there is absolutely nothing there right now. We have discovered a very thin filament of about 60 galaxies in this void. But they are so sparsely distributed that if the Milky Way was in the middle of Boötes void, we wouldn't have known other galaxies existed until the 1960s due to the distances. So, there you have it. That's what Boötes void really is. A very empty patch of space, hundreds of millions of light years across, containing some very lonely galaxies.
Thanks for watching. I really want to give a huge thank you to our astronauts on Patreon. It's really becoming a thriving community, and I've loved reading all your messages and comments over there. If you'd like to join in, then you can visit the link in the description to become an astronaut and bring the channel more stability than the algorithm. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.